engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
Questions. Research.
technology.
Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, Happy New Year, and welcome to The Naked Scientists, the show that brings you the biggest breakthroughs and talks to the major movers and shakers in the worlds of science, technology, and medicine. I'm Chris Smith, and today we're returning with Titans of Science and the team who have successfully treated Huntington's disease for the very first time. In this episode, we're hearing from not one, but two Titans of Science together, and that is because Ed Wild and Sarah Tabrizi are neuroscientists and neurologists, as well as long-time collaborators based at University College London. And they've devoted much of their careers to understanding Huntington's disease. This horrible inherited condition usually lurks silently in the genome until a person reaches their late 30s or early 40s, before it begins to rob them of their personality, mobility, and ultimately their life. Historically, we regarded it as only something we tried to manage or support rather than actively treat. But now, thanks to Sarah and Ed, that's changed. The gene linked to the disease has the unusual characteristic of carrying a number of repeated genetic letters, in this case C, A and G, and if there are too many of these repeats, they cause the build-up in the brain of a toxic piece of protein. But because we know which bit of the brain is chiefly affected, it's been possible for Ed and Sarah to develop a gene therapy that works by cancelling out the broken Huntington's gene message and slowing the disease down by over 70%. And that's in patients who are already showing symptoms. Treatment at an even earlier stage might yield even more impressive results. I went to see them in London.
Huntington's disease is an inherited genetic dementia. It's a rare disease. It affects about 1 in 10,000 people throughout the world, but it's a devastating disease because it's a disease both of individuals and families because of its genetics. And it causes a neurological condition that's characterized by funny extra movements, also speech problems, swallowing problems, progressive thinking problems and dementia, and prominent psychiatric symptoms. And so together, it has been said that it's like a combination of Alzheimer's disease, Parkinson's disease, and schizophrenia, which I actually think is a good description of the way it causes symptoms of the disease.
Although, unlike those aforementioned diseases, this comes on much younger, doesn't it?
It does. The average age of onset in the world is 42 years old. So it affects people in the prime of life, and it's genetic. So if you have an affected parent, you have a 50-50 chance of inheriting the Huntington's disease gene and developing the disease yourself.
Is it all over the world, Ed? I mean, if we look geographically, do we see this cropping up in populations everywhere?
it's everywhere that it's been looked for. It's certainly more common in some places. So it's weirdly common in the highlands of Scotland, but the most famous cluster is probably in Venezuela, where it's hundreds of times more common than it is in Europe, and it's common elsewhere in Latin America as well. There's probably not as much in Asia, East Asia in particular. However, it's not clear how much of that is a real biological thing and how much of it is that there's a lot of stigma associated with the disease, so it sort of gets covered up and swept under the carpet.
Often when we see neurological syndromes and then we look back in the history books, there's a famous neurologist, often a Parisian one for some reason, who has described this back in history. Can we find this documented back in history, or is it a more modern diagnosis?
The guy who attached his name to the disease, George Huntington, to be fair, he did publish the first paper on the condition, although he'd inherited a GP practice from his dad on the east coast of the US. It's not really clear whether anyone else had actually described Huntington's disease before that. It's possible that Charcot had, but hadn't given it a name. It's debated. And there are these strange episodes in history where people started moving in involuntary ways, and a lot of it turns out to be psychological, but behind some of these mini sort of waves of involuntary movements there may have been a seed of Huntington's disease.
So when, Sarah, did people realise it was probably linked to genetics?
Well, actually, in George Huntington's original paper, he wrote one paper at the age of 21 when actually he was still a medical student at Columbia University.
When was that?
In 1872. And in that paper, he really, and this was before Mendelian genetics and Mendel and his peas, he wrote, if the children of the original Shakers are free from the disease, then the thread is broken. So that is a clinical medical observation really before we knew anything about genetics and Darwin and Mendel, really describing the autosomal dominant inheritance of the disease, which means if your parent managed to escape the disease, then you were free of the disease. And that was in the original 1872 monograph.
Because indeed we say, well, there's a 50-50 chance, isn't there? If you've got a parent who's affected, there's a 50% chance as their child, you will have this.
That's right. And that's part of what makes the disease a disease of families as well as of individuals because of the 50-50 chance of inheritance. So many people will watch and look after an affected parent die of Huntington's disease, knowing that they are at 50-50 risk themselves, so they know what is ahead. And about 20% of those people at risk who have a family history decide to choose genetic testing. And it's called predictive testing to find out if you carry the gene that affected one of your parents and that you will get that disease as well. And about 20% of people go for that predictive genetic testing.
When did it get linked to the nervous system? In other words, when did people realise that this condition had a brain basis?
That's a great question. I hadn't thought of it that way before. I think it must have come with George Huntington and his original description. The time when people might have thought that involuntary movements or psychiatric problems came from somewhere else, like the heart or something, was probably long gone by the time George published his paper. So I reckon probably around about that time, it would have been obvious that the brain was where most of the symptoms were coming from. Although, to be fair, what we know now is that it's actually a disease of the whole body because the gene that causes it is everywhere and is active everywhere in the body. And that may be one of the reasons why we see things like weight loss in our patients with Huntington's.
Around the time of the turn of the century, the last century, that's when neuroanatomy really began to take off. People were making beautiful sections of brain tissue. They were drawing these things in exquisite detail. So presumably they would have gone into the nervous systems of people who showed these traits and started to have a look. So when did they realise which bits of the brain were being affected?
Well, once you know that someone has Huntington's disease and they die, the brain will look very different. Some of these patients would have gone for post-mortem examination of the brain, and at that point it would have been obvious. The whole brain was smaller than the brain of someone who died from something else, but the deep part of the brain, which you call the striatum, because it's stripy, and striatum is a Latin word that means stripy, is the place where the cells that are particularly affected by Huntington's disease live. And so if you imagine looking at a slice of the brain, there's a bit in the middle that looks exactly like the two wings of a butterfly, but black. And those are called the ventricles, and they're full of fluid. Right next to those, there should be a chicken nugget-sized piece of brain called the striatum. And in people with Huntington's disease who've died from the condition, that's nearly gone. And it gradually melts away because those brain cells are dying as a result of the gene.
And which brain cells are in there, Sarah, which are selectively vulnerable? They die off preferentially in that region of the brain that Ed's just been talking about.
So the brain cell that dies off early is actually called a medium spiny nerve cell. And the reason it's called a medium spiny nerve cell is it has spines around in the cell body. And those spines project to the cortex, which is the outer part of the brain, which is the way we think and move, is controlled mainly by the cortex. And those neurons or brain cells in the center of the brain project to the cortex. Those are the brain cells that die very early in the course of the disease.
And why does that translate into the symptoms that we see?
Because those nerve cells in the striatum, or the deep structure of the brain, also control our movement. And when they stop working, they lose the ability to control other parts of the brain. And that results in the extra movements and the involuntary movements. And The word chorea is often used in the association with Huntington's disease. It used to be called Huntington's chorea. It's now called Huntington's disease. But chorea comes from the Greek word to dance. And it's because the movements associated with Huntington's disease look like someone is in dance-like movements. And that's because the inhibitory part of the brain that stops you having these extra movements is lost early in the disease.
And is that also involved in behaviour, which is why you get these psychological and psychiatric changes with people as the disease progresses?
Absolutely. So it's involved in reward. The areas involved in impulsive behaviour, attention, concentration. They're all features very characteristic of Huntington's disease.
So people saw the symptoms, realised it ran in families. They could pin it on a bit of the brain. But when did they link it to a gene, Ed?
1872, the paper was published describing Huntington's disease. It wasn't until 1993 that the gene that causes the disease was discovered after a decades-long effort, which was actually initiated by a family with Huntington's disease, led by Nancy Wexler, her sister Alice, and their parents. Nancy's mother had been diagnosed with Huntington's disease, and her father, who was a Hollywood psychoanalyst, decided to enlist all of his celebrity friends to set up the foundation that then became the engine behind identifying the gene that caused Huntington's disease. And along the way, incidentally, more or less invented all of the tools that we then use to decode the human genome for the first time. So it was really like that scene in the Wallace and Gromit movie where their dog is on the train and he's laying track furiously from the front of the moving train. That's exactly how it went. And it was one of the first genes to be discovered for a neurological disease. And everything changes overnight once you have a gene with a known cause.
There's something interesting with that gene, though, isn't there? Because when people looked at the gene in a healthy person and a Huntington's person, actually the gene itself looked okay. And that was part of the reason why they struggled to find it in the first place, wasn't it? Because it didn't actually have a difference in the gene message. There was something else next door that was where the exciting stuff was happening.
Exactly. The most common genetic spelling mistake that leads to illnesses would be the addition of a single extra genetic letter, or a deletion, or a substitution where one letter changes from one to another. And occasionally you get something bigger happening, like a big chunk of DNA that's missing or has been taken out and put into the wrong place by mistake. In Huntington's disease, and subsequently in a number of other diseases, particularly affecting the brain, the genetic difference is an unusual quirk. Everyone has 2 copies of this gene, one from mum, one from dad, and each copy of that gene contains a number of repetitions of the genetic sequence, which we denote as CAG.
They're the genetic letters, aren't they? C, A and G. They're just a triplet of genetic letters. But you're saying that there's a variable number of those inside the gene.
Exactly. Every human Huntington gene has a number of CAGs at the beginning, and it's usually between 15 and 20. Huntington's disease happens when a person has 36 or more of those repeats. And typically, a person with Huntington's will have between 40 and 45 repeats. So it's very much too much of a good thing. This is an important gene. It's a recipe for an important protein, and the protein is a machine that does important stuff in the brain. But when you have too many of these CAGs, something goes wrong, and the protein becomes toxic.
When you look at those CAG repeats, Sarah, why do some people have more of them then? Why is that magic number 36 important, and why do people with more of them have a problem?
Because when you inherit 40 or more of the repeats, you will always develop the disease. So if you live long enough and you have 40 or more repeats, you will always develop Huntington's disease. And it's what we call fully penetrant, which means that if you have the gene, you will definitely develop the disease. And so there's a lot of study of how those extra repeats make the protein toxic. And it looks like just having those extra repeats causes the ability of the protein, when it's in the brain cells, before the protein's made, is that the piece of DNA that forms the message, that piece of DNA, those repeats get bigger in the brains of living patients. And so you may be born with 40 repeats, but what we now know drives the disease is that repeat grows during your lifetime, and it can grow up to several hundred or even thousands of repeats in the nerve cells that die. And we now know that's the first event in causing the disease. And that probably happens decades before people show signs of the disease.
Does it matter if you inherit it from mum or dad? Because there were claims that some diseases are more likely to happen if you get them from one or the other parent. Does Huntington's disease do that?
There is some relationship, because if you inherit it from your dad, there is the possibility that you can have younger onset. And that's because the repeat is unstable when sperm are being made. So sperm are rapidly dividing. They live for about 120 days. But because they're replicating all the time and they're replicating their DNA, part of what happens in sperm is the repeat in sperm can stutter. And when that stuttering occurs, the repeat can get bigger. And that means if that sperm then fertilizes an egg, that sperm can then result in a child with a longer repeat. So that's what we call genetic anticipation. And it's most common through the male line because of the instability of the repeat during the production of sperm.
What does that repeat do in nerve cells, though, Ed? Why should just having some extra genetic letters, and it seems that just having them there isn't the main thing, because you can have 15 of them and you're fine, you have 40 of them, now you're not. So what's the difference in those two circumstances? How does that translate into disease?
It's important that there are 3 letters repeated, because one of the rules of biology is that a sequence of 3 letters in your DNA will translate into one protein building block. And CAG happens to be as an instruction to the cell whenever it's making any protein. When it sees that CAG, it knows that what it needs to do to make the protein is add one building block called glutamine. And the protein only works if it has, in humans, if it has those glutamines in it. And actually within the normal range, say between 10 and 25, if you have slightly more CAGs, your cells may actually be a little bit more efficient at producing and using energy. So that's probably what the evolutionary drive is for this the number of CAGs to grow. Unfortunately, when you start to get too many, 2 bad things happen. The first is that the starting number, the number you're born with, is a key determinant of the rate at which the CAG might increase during your life. So if you start with a normal CAG, it's very likely that all your cells will keep a normal CAG by the time you die, even if you die of old age. If you start with a big CAG, that not only causes bad things to happen in the cells, but it is also a ripe situation for the CAG to get even bigger. At the protein level, what's happening is that all of those little glutamines that are extra, that shouldn't be there, too much of a good thing, change the shape of the protein, and they make the protein sticky. And once proteins become sticky, they stick to each other, they stick to other proteins that are there to do useful stuff. And what you end up with is this sort of bull in a china shop that's going around messing up all of the delicate, important things that our cells need to do. And actually one tiny bit of the protein is produced independently, and so you get this little tiny bit of really harmful protein that is then able to get into the nucleus of our cells where the DNA, where the genes live, and it actually messes around with the switching on and off of genes, a little bit like an elephant getting into the control room of a nuclear power station. Chaos ensues.
Is this why, Sarah, that despite that gene change being there from the minute you're conceived, it takes until the average age of 42 before this kicks in, because this stuff has got to build up? And it's got to build up to a level in a cell that begins to then do harm, and then it's got to do enough harm before we begin to notice the consequences.
Absolutely. So that was one of the unknowns, that we didn't know why the disease occurred in your 40s when you were born with the mutant Huntington gene. But we now know every part of the jigsaw. You're born with the mutant Huntington gene with these extra repeats, and those with the extra copies of that repeat who have Huntington's disease, that repeat gets bigger in the brain cells that are vulnerable. And that results in the toxic sticky protein, as Ed described, that causes all the problems in the cell. But what we know is that repeat slowly grows in brain cells, and when it gets to about 150 repeats, it starts this big cascade of toxicity in nerve cells, and the nerve cells soon after that begin to die. And now we know that process is quite slow to go from 40 to 150 50 repeats, but once you get to 150 repeats in brain cells, the process is really fast. You get very toxic fragments of protein being produced that cause the nerve cell to die fairly quickly. And we now know that growing of the repeat is modified by DNA repair genes. And so DNA repair genes are big news in cancer. Many cancers are caused by abnormalities in DNA repair genes, but we now know that brain diseases that, like Huntington's disease, have a link also to DNA repair genes because they are like the police of the genome. So what those DNA repair genes do is they check your DNA all the time. As we sit here, our DNA is accumulating mutations. And what DNA repair genes is they fix them. But what happens in Huntington's disease, those DNA repair genes do their job too well, and they keep trying to repair the repeats. And in that repairing of the repeats, they make the repeat get bigger. And that's now all the different parts of the jigsaw. We now know we need to target DNA repair genes to stop the repeat getting bigger and to target ways of switching off the mutant protein. So in terms of the disease, we really know from A to Z how it begins and how it causes disease.
Presumably this is going on all around the body, Ed. If this gene is on in all our cells, are all cells vulnerable to some extent?
It may be true in theory that all our cells are vulnerable, but it's clear that the brain is much more vulnerable than anything below the neck. And within the brain, it's the brain cells of the striatum that are particularly vulnerable. I think that is one remaining mystery as to why that part of the brain is so vulnerable to these expansions in the CAG getting bigger and the effects of that on the protein and the harm the protein causes. But it's an interesting question. One of the things, if we manage to treat Huntington's disease in the brain, one of the things we might end up seeing is a form of Huntington's disease that only affects the body. I'd love to get into a future where that's something that we get to see, because it feels to me like that would be less bad than having Huntington's in your brain and also an interesting problem to deal with.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound, perfect music for audio and video productions.
This is the Naked Scientist podcast with me, Chris Smith, and today Ed Wild and Sarah Tabrizi, who are tackling Huntington's disease, are our guests on Titans of Science. So Sarah, you've now got to a stage where you've taken the learning and you think we understand the mechanism by which this disease manifests, notwithstanding the fact that there might be other things happening more slowly around the body and people at the moment aren't living long enough to see what they are. We hope that one day they will. That's what Ed's saying, isn't it? How did you think, though, we might be able to treat this?
So one of the things that we've been working on, Ed and I have been working on for a long time, is how can we switch off the toxic protein? Because there were many different approaches trying to clear proteins, to remove sticky proteins from the brain, but none of them worked. And I think the reason for that is that they were quite far away from the primary process of why nerve cells die. And why nerve cells die is because there is an abnormal piece of DNA, it causes an abnormal message, and then that message codes a toxic protein that then gums up the system. So we started work in 2010 with Ionis Pharmaceuticals, and they were experts in developing chemicals to try and switch off bits of DNA. And we then worked with them to try and design a chemical piece of DNA that would bind to the Huntington message and switch it off. And this is a piece of DNA, and it's modified in a chemical way to make it stable and to also make it that you can inject into people without you having an immune reaction in the same way that if you had a viral infection. So we took the piece of chemically modified DNA, it binds very specifically to the Huntington message, and then tested it in animal models. It worked. It switched off the Huntington message and the protein. But it was how to get that to the human brain, and that was the big challenge. And so we worked on developing a way of putting this into spinal fluid doing a lumbar puncture to try and get the piece of DNA to the brain. And spent a long time trying to work up the lumbar puncture protocol, but it was successful. In 2017, using this piece of chemically modified DNA injected directly into spinal fluid, we found that we could switch off the Huntington message. And that was measured by measuring the protein in spinal fluid of affected patients.
Presumably, though, that's only going to be a temporary effect. When you keep putting the stuff in to cancel out the gene activity, it will work. But as soon as you stop doing those lumbar puncture injections, it would come back.
That's exactly correct, because it was reversible in that you could infuse it. It lasted about 2 or 3 months, and then you had to do another lumbar puncture and inject it again. But when we started, no one had done this before, and they hadn't tried this for an adult brain disease. So one of the good things about it was that it was reversible, and that we knew that if it was going to have really bad side effects, in 2 or 3 months it would be out of people's systems. But it worked. It worked by lowering the toxic disease-causing protein. But drug development is difficult. It's never straightforward, and the journey of the piece of DNA, chemically modified DNA, is still ongoing. And it's still in trials, and it's still being tested. And next year, we hope that the big trial will read out, and we'll know whether it slowed progression of the disease in patients who've been treated with that piece of chemically modified DNA to switch off the gene.
An important stepping stone, though, nevertheless, isn't it, Ed? Because it says, if I could get this to be on all the time, I could potentially slow down the disease. And is that what was in your mind as you took this forward?
Exactly. I talk of a big breakthrough like that, the first time that we show that we can tell the brain to make less of the thing that's harming it. I talk about save points from computer gaming. So in some computer games, you have to sort of reach a bonfire or a place where you can save your progress. And once you've done that, whatever happens next, even if you die or something goes horribly wrong, you only have to go back to that point, not to the beginning of the game. And I feel like 2017, lowering production of the Huntington protein was the first big save point, honestly, that we'd had since 1993. After 93, we knew what the cause of the disease was. From 2017, we knew we could lower the production of the protein, and all that was necessary was to do so in a way that would make a difference to the clinical progression of the disease and, crucially, hopefully, be as safe and convenient as possible for patients. So the dream really is a cure, which different people use that word differently. But among other things, it's probably going to be something that has a big effect that you only have to do once, and you could potentially do early on, and then that person would be disease-free or would have a relatively normal life compared to if you hadn't done that.
Are you at that point?
What's different about the latest approach is that it's a gene therapy. So the principle is the same. We're trying to reduce or turn off the production of the harmful protein. But with a gene therapy, you reprogram a virus to become the treatment. You inject it into the part of the body where you want it to be, and once it's there, the virus reprograms the cells that it meets, in this case, brain cells. And once that's done, if it's successful, the effects will persist in theory for the entire life of the person. And so far there's no signs that these viruses, once injected into the brain successfully, will ever wear off. They might do, but we haven't seen it yet.
You are actually doing this, aren't you? I mean, you have made viruses that have got that genetic mirror image of the Huntington gene and appears to cut down production, and you've put that into patients. How many people has it gone into, and what has happened so far?
So the total number of people treated is 42. It's been in the US and in the UK. And in the UK, it was a neurosurgical procedure, took between 12 and 20 hours. And the virus carrying its DNA treatment was injected directly in a neurosurgical procedure into the deep structures of the brain. It was a long neurosurgery. It was all done at the Advanced Therapy Centre in Cardiff, a very brilliant neurosurgeon called Professor Liam Gray, who did all the surgeries in the UK. And the virus is injected directly into the deep structures in the brain. It then infects the cells. It then turns the cells, as Ed said, into mini factories producing the treatment forever. And then it also spreads throughout the brain and switches off the production of the toxic protein throughout the brain as well. And because it's a virus that delivers the piece of DNA, it's there forever.
And the outcome? So when you do this, if you follow these patients up, how much time now can you look back in the rearview mirror and what's been the difference?
So this was 3 years of follow-up. So in 12 patients at the high dose, in those people, there was slowing of their disease progression by 75%. And it was slowing of the measures that we use, such as the ability to work, the ability to drive, the ability to manage your money, the ability to look after yourself. That measure was slowed by 75%, and we haven't seen that in any study. But in addition to that, over 3 years, there was also evidence, measured in spinal fluid, of a protein that is a measure of the health of a nerve cell. And in brain diseases like Huntington's disease, that protein called neurofilament goes up because it's a marker of brain degeneration. And in this study, that marker was dropped by about 30 to 40% after 3 years in those people treated. And the only way that could have happened is it shows that nerve cells are being saved, and it shows that the viral gene therapy was working to slow the disease.
If that protein, Huntingtin, is really important in health, not in Huntington's disease, but a healthy person needs it, and you've come along and turned it off, what might be the consequences?
Well, it doesn't turn it off completely. It lowers the level of the wild type, and the wild type protein is the normal protein. It lowers the level, but in the subjects, by lowering the toxic disease-causing protein and also that tiny fragment that Ed mentioned, that really gums up the system, it lowers that as well. And by getting rid of the bad toxic proteins, it's allowing the nerve cells probably to recover a bit, and they cope, I think, with a lower level of the normal protein. But we're not switching off the normal protein, we're lowering it. So on balance, you're getting rid of the bad guy without lowering too much of the good guys. And that has had a huge difference on disease progression. I mean, 75% slowing over 3 years was much more than we expected. It's in a small number of people. It was the high dose in 12 people, but it's supported by an objective measure of the health of nerve cells, so we can have confidence in the result. What we now need to do is treat more people, try and get the drug licensed in the UK, and do more studies to test this in larger numbers of people.
How did the patients respond or react when you said 20 hours of surgery to put in a virus into your brain, which we hope might make a difference to your disease? Were they up for it?
The Huntington's disease community has continued to astound me with the things that they will do and will subject themselves to, and they're not doing it for themselves. This is a family illness. Most of the people who volunteer to take part in our research and clinical trials are doing it for other people, their brothers, their sisters, kids, grandkids. It's an extraordinary community and an immense honour to have been part of it, an honorary member of the Huntington's disease community. So the normal reaction to saying, I want my friend in Cardiff to drill into your skull, put little plastic tubes into your brain and inject a virus into there would be, please don't ever speak to me again, I'm blocking your number. When you say that to someone with Huntington's disease, the response is much more likely to be, where do I sign up? I'm free tomorrow, can we do it then? I want to do this for my kids. That's a bit of an exaggeration, but this trial is no exaggeration to say that the first few people who volunteer to have brain surgery for a gene therapy that will change the DNA of their brain forever are at least as brave as Yuri Gagarin and the first few people to get on rockets that might have blown them up on the launch pad. An extraordinary act of human generosity, and the impact on the HD community and the whole human race will be felt for generations, and it's thanks principally to the people who volunteered.
The people that you've enrolled to start with were presumably already becoming symptomatic, and you got a 75% response. People often say with many of these degenerative diseases, we're often trying to slam the door after the horse has bolted. So is your feeling that if you'd gone in even earlier, you could have gained even more.
We saw the results a month before everything was announced. We were in a meeting, we saw the results, and it was very clear when you looked at the graphs that there was a huge difference between the treated group and what was natural history data. And it was, wow, this has worked. So it really was. And actually, we weren't allowed to tell anyone at all until the 24th of September. So I think the only person I told was my husband. And I swore him to secrecy. But it was really, after working in the disease for nearly 30 years, it was that point where you think, oh my gosh, this disease is potentially treatable. And it was also in people with early symptoms of the disease. And so you're absolutely right. We were beginning to think that by the time you developed early symptoms of the disease and you were having to give up your normal job, that it was going to be too late to treat. That's one of the things about brain diseases that we were beginning to worry about. I was really beginning to worry about. But this showed that even when you've got symptoms, if you target the right toxic proteins, you can slow the disease. So what that means, though, is if we go earlier with people who carry the gene but are healthy, and we're following a large cohort of young adults who carry the gene but are decades before onset, I hope that we will be able to prevent the symptoms ever occurring. And that would be the nearest to a cure that you'll ever get. But that's what we hope to do. We want to try and develop a therapy that doesn't need 20 hours of surgery or 15 to 20 hours of surgery, that does what this therapy does, but that can be given in a more accessible way, that doesn't involve complex neurosurgery, and that we can give it to people who are well, who carry the gene, who are completely well, and we hope that we can stop and prevent the disease. And that's the goal for the future.
We're getting together just before Christmas, and this came obviously in the autumn, but it's a really nice Christmas present, isn't it? You must think 2025 is going to be marked up in your neurological calendar as a good year, Ed.
It really is. I mean, I've been doing this less long than Sarah, only 20 years. But you sort of get used to giving people bad news that has a little bit of good news hidden within it. The trial was negative, but we learned how to run a better trial, but we found a new biomarker, or, the trial was negative, but there's another trial coming in, 18 months. To be able to say the trial worked, the drug slows the progression of Huntington's disease, the amount of slowing is 75%. It's a one-off treatment, and this treatment, if given early enough, could entirely prevent the development of Huntington's disease in people who've been born with that expanded gene. I'm not someone who easily becomes lost for words, but I do not have the words yet to describe how much of a positive outcome this is, except to say that there are brilliant scientists, many, many, many times smarter than me, who worked much harder than me their whole careers and died of old age, having done nothing wrong, and never got to see a breakthrough like this. So this is a Christmas present from the Huntington's disease community to itself and to the world. And I do think that we will look back and think this was when we really started to see things heading in the right direction.
It is a wonderful story, and that brings a lot of hope to a lot of families. Thank you very much to our Titans of Science this week, Ed Wild and Sarah Tabrizi from University College London. That's it for this episode. Do join us on Friday, though, when we're going to be unpacking the tech behind the precision operation by the US to capture Venezuela's president, Nicolas Maduro, and do vegan and vegetarian diets have a health impact on young people? What do the studies say? The Naked Scientists is supported by Rolls-Royce. I'm Chris Smith, and from all of us here at the Naked Scientists team, thanks for listening, and until next time, goodbye.